So welcome to the Soil Science 312 Soil Fertility and Fertilizers soil sampling video. Today, folks, we're out at the Goodale Farm, the University of Saskatchewan Goodale Farm. This is where the 312 students normally go on their soil sampling field trip. What we're going to do today is we're going to take a look at some soil sampling equipment, different equipment that you can use to take samples of soil, and just look across the field area and talk a little bit about soil sampling strategy to complement what we've talked about earlier on when we talked about soil sampling to account for variability in an earlier lecture in the class. So let's talk first about hand sampling tools. So for hand sampling tools, there are some different tools that are available for hand sampling soils. One of these is what's called the Backsaver soil probe. And what we can do with this is we can take it out into the field. So we've got a 30 centimeter sampling tube on the bottom of this device, and we can mark this and we can use this to obtain surface samples. So normally something like this would be used to obtain samples of soil from a 0 to 15 or a 0 to 30 centimeter depth. Going deep with this type of unit doesn't work particularly well, but for surface samples, we simply would take this and push it down in to the soil. Pull it back out. There we've got a 0 to 15 centimeter increment of soil. And then we remove that out of the tube and put that into our sampling bucket or container in which we're collecting our soil samples. So that's one way to get a sample of soil out by hand using the Backsaver probe. We take that out and we dump that into a bucket. In a bucket, we would have a number of different cores from the area that we're sampling. We mix them up and we obtain a composite sample from that. The other sampling tool for hand sampling that works pretty well is called the Dutch auger. So as you can see, it's a tool kind of like a small fence post auger. And what we have here at the bottom is a little auger, and it's marked so that you can take different depth increments. So when I go in here, folks, I take this and I simply twist it. And there's my sample of surface soil, in this case a 0 to 15 centimeter sample, and I can take that and remove that from the auger and put that into my plastic container that I am using to collect the samples that I'm taking out of the field. Now the other hand sample, I guess the other thing I would say about this is you can go deeper with this, and that's why we got these marks on here, because you can go back into this hole and very carefully go down in and get the next depth increment. So, provided that the soil is not too hard and too difficult, with a unit like this, you could go down 1 foot, 2 feet, even 3 feet. I know in some sandy soils with extensions on this, we've been able to go down as deep as 6 feet with extensions and get samples down deep from within the soil profile. The other hand sampling unit, and I'll get you to pass that to me, Stephen. Thank you. Is a good old-fashioned shovel. And a shovel, folks, is very good for getting samples of intact surface soil, especially where you want to have the structure of that soil and its physical condition maintained more or less intact. So we take shovels of soil, surface samples of that, and we can use this sample like this to look at things like soil aggregation, structure of the soil in a relatively intact state. Now the other approach that can be used, in a sense, in a way to get a sample of soil in the field, so to speak, is to use these plant root simulator or PRS probes. And we've talked a little bit about these in class already, and we'll talk about them a little bit more later on in term. These are plant root simulator probes which contain ion exchange resin membrane in a membrane or sheet form. So that surface there on this orange probe contains positively charged sites that will absorb nutrient ions like nitrate, phosphate, and sulfate from the soil that comes into contact with it. And this purple probe here is a cation exchange resin membrane, and it has negatively charged surface on that membrane, and it absorbs nutrient cations like calcium, magnesium, potassium, in which the soil is in contact with that membrane. So folks, in some of our research work, what we do is we go out and we take these probes and we place them directly into the soil and allow them to remain there for a period of time. And as they sit there in the soil, the nutrient ions that are in contact with that membrane and a little bit further away diffuse to that surface and become absorbed onto the surface by ion exchange. Then, after a period of time, we may leave them in the field for as long as 2 weeks. We pull them back out. We wash the soil off of that membrane, and then we strip the ions off of that surface into solution, and we measure them. What commercial lab, Western Ag Agronomy Laboratory Services, that they do is they take a sample of soil out of the field that's in a bag, and they place that probe into that sample of soil in a bag in their laboratory. So they measure supply rates of nutrient ion using the PRS probes for farm fertilizer recommendations on samples of soil that are submitted to their lab, and they measure the supply rate, and they stick that probe into a bag containing the soil. So in their approach, where they're measuring nutrient availability in farm field samples, they're measuring it in samples that are submitted, that are brought into the lab, and the PRS probes are placed into that sample, and the supply is measured under controlled conditions of moisture and temperature. We talked a lot, folks, about variability earlier on, and we can have certainly across a field area like this, macro scale variability. So as we look across a field area like this, the first thing that we see as you look towards the south there is you see we've got two fields here. We've got a canola stubble field. A little bit further on, we've got a barley stubble field. Obviously, those fields, different stubble types, are going to be sampled separately. Within any of these field areas, you can also see topography. We're in an upslope position in this field, and as we move towards the south, you can see the elevation decreases. We move into a mid-slope area about 20 or 30 meters from here, and then down at the edge of the field boundary, we're starting to get into a lower slope area. And when we look out a little bit further into the barley stubble, we can see there an area where there isn't as much stubble. We see some grass that's been seeded down a little bit further on. That's a part of the field that actually is affected by salinity. Folks, we've moved from where we were on the upslope portion of this field on the canola stubble, downslope into this barley stubble field. So this is a kind of an area. It represents only about maybe, in this whole field, as you can see, maybe only about 1 or 2% of the whole field area. If you're using traditional composite sampling across this field area, you would want to stay out of this area. You want to stay out of this area because it's an area that's affected by salinity. Farms put fertilizer on here. There's been, over the years, very little crop uptake. So these saline or salt-affected areas of the field, because of little crop growth and removal, oftentimes have quite high available nutrient levels. And they also have lots and lots of sulfate. Why would these saline areas have huge amounts of sulfate? Because the salts that cause salinity in Saskatchewan are sulfate salts. So anytime you have a little bit of salinity in the soil, that is associated then with very large amounts of sulfate salt. So if you were testing this soil for available sulfur, if you took even just one core out of here and mixed it with the rest of your cores, you would have a composite sample that ran very, very high in available sulfur. Yet perhaps maybe 90% of the field was sulfur deficient, but because you had that one core in here from this very high area, it skewed the value of the composite and gave you an erroneous indication of what existed in terms of sulfur availability across the field. So that's why you want to stay away from this area, and maybe you would, if you were interested in managing it separately, just take the saline area, identify it, and sample it separate from the rest of the field. And so in a zonal type approach to sampling, where we're looking at using that directed or smart sampling approach that I talked about, we could divide this field up into zones based on the topography, based on the electrical conductivity, number of different approaches that we've talked about and go in and sample those zones separately. If you're looking to get an idea of the general fertility across an area, we talked about the traditional composite sampling approach, where you go across in a zigzag pattern and take cores at random. So you could start out with this probe, use the back saver as an example, and just start to walk across the field at random, taking cores out as you go across the field area that you're interested in getting an indication of the fertility on by taking a number of different cores from different locations and combining them into a pail and getting a subsample that represents an average of the area that you've taken your samples from. Of course, we talked about wanting to stay away from atypical areas, unusual areas when you're doing that composite traditional sampling approach. So areas that you'd want to stay away from that may skew your results if you were combining a number of cores into a single pail and taking a subsample. Areas that you would want to avoid would be, for example, those saline areas. You may want to instead sample those separately. You'd want to stay away from the roadside area next to the ditch. Also, the approach area where folks might be filling their seeders and may end up spilling some fertilizer. You took one core out of there and mixed it with the rest of them. You could have a sample that had a skewed value, that overall the average was much higher than what existed in most of the field area. So we do need to be cognizant of variability on a macro scale and try to account for that as we talked about earlier on. Finally, I'd like to talk a little bit about microscale variability. Microscale variability, what we're talking about, folks, is variability that exists only over a few centimeters in the field. And in fact, that microscale variability over only a few centimeters in the field, we found in some of our previous research, can be as high as the variability that you might encounter in available nutrient across a few or several acres within that field. And that microscale variability over a few centimeters, oftentimes is explained by things like residual fertilizer bands. So that in the fall of the year, you may still have some unused fertilizer in a side row band or a mid row band, especially phosphorus maybe, that is unused by the plant, and it's still present in that band. And so if you went out and you systematically took cores in that field every time from where that old fertilizer band existed, you would overestimate what was there as far as the residual available nutrient in the soil. So to best account for this microscale variability that exists, and to do a good job of accounting for it and getting a true representative sample, what we may do is we may take a slice of soil across two seed rows so that we get the seed rows and the area in between in our composite sample. Now you need to take a lot of samples if you're doing this, and a lot of soil comes out of the field, but it does account for that microscale variability where you got a band, an old fertilizer band there, no band there, another old fertilizer band there. When you get the whole big cross-section of the soil, you've got it all there together in your sample, and therefore account for that in your analysis. So microscale variability, folks, is something that we also need to be aware of and think about when we're sampling. And certainly if we're going across a field area or a zone and taking cores, we do not want to systematically just sample the seed rows because it's easier to get the probe in. We want to make sure that we're getting that sample from that area at random, and if we're going to try to do the best job of accounting for that microscale variability, we best maybe sample right across that seed row area so that we've got all of that soil in our sample that we're going to end up being analyzing. So folks, after we've collected a number of cores from the area or the zone that we're interested in, collected a number of cores and put them in the sampling pail, then what we need to do is we need to get a representative subsample of soil out of that pail into a container that we're going to send out for analysis. So in this case here then, I got a pail full of soil here that we've collected from a number of different locations within the zone. So we would go in, we'd mix that soil up well, mix it up well, take a subsample, and in it would go into the container, a plastic bag, or it may be a paper bag, or a bag, a cardboard type bag that's lined with some type of a plastic. And that soil then is what goes into the analytical lab for analysis. We've talked about soil testing, what happens after that sample gets into the lab, the analytical techniques that are applied to it. We've covered that, and we're also going to provide you with a video of that as well, a little bit later on in the class. We also talked about the importance of proper sample handling, folks, so that when you've got that sample out of the field, you do not want to put it on the dash of your car and let it sit there for 2 weeks before it gets sent in. What happens if it sits there warm and moist on a dash or a trunk of a car for 2 weeks? You're going to get mineralization taking place that doesn't represent what's going on in the field. And you're going to get an artifact in your sample analysis as a result of that. Perhaps unrealistically high available N content as a result of the way that the sample is handled. So what normally happens after samples are taken out of the field, and what we do in our research work at the University of Saskatchewan, we sample many plot areas in the fall of the year. We deal with probably 3,000 or 4,000 samples every year. These samples that we collect that are bagged, we bring them in from the field, and we may put them into a freezer to freeze them until we have time to take them out and process them. The other way that we preserve the sample, we can freeze those samples. We also dry them. So we lay the samples out and we air dry them at about 30 to 40 degrees centigrade, and that dries the sample out, and that also preserves the sample. Ideally then, and you want to get that sample once it's been processed, to get it into the lab and apply that analytical technique as soon as possible. If you're interested in characteristics like that are related to microbial activity, biological activity in the soil, the best thing if you're interested in biological activity of the soil, things like microbial respiration, microbial populations, rather than freezing the soil or drying it, which can alter the microbial population and its composition, rather than freezing or drying the sample, if you're interested in soil biological properties, microbial activity, population composition, and so on, what we would do is take that sample and chill it. Put it into a cooler and keep it at about 4 degrees centigrade, and then use that sample, ideally also undisturbed, unaltered, not mixed up, but pretty much intact out of the field, chilled down to 4 degrees centigrade, and use that sample for our analysis of biological properties. Now, been talking about hand sampling so far, but the reality, folks, is that a lot of the samples that come out of the field, certainly in our research program, and samples that folks at ag retailers and other folks, crop consultants who are doing custom soil sampling, chances are they're not doing a lot of hand sampling with tools like Backsaver probes or Dutch augers. Instead, they're probably doing a lot of their sampling or all of their sampling with a hydraulic punch unit like you can see here. This is a Giddings hydraulic soil punch or soil probe. The basic concept by which this works that you'll see in action, we've got a tube here, and there are tubes of different sizes that we can hook onto here. We got a big hydraulic ram there, and Stephen here is going to start it up and show you in just a moment how it works. But what we simply do is use that hydraulic pressure to push that tube into the soil and pull out and get a core of soil out of that field to the depth that we're interested in. And as I said in lecture when we were talking about this, we use this a lot to go down sampling a foot, 2 feet, 3 feet. You can get down probably as deep as 6 feet with this under good conditions. If you want to go really deep down, down into the and start to look maybe at hydrology, then you're going to need a drill truck. But for most of the purposes of soil sampling for assessment of nutrient availability, this unit works good to get down to the depths that we're interested in. So I think probably, Stephen, the deepest that we've gone to this would be 180, maybe 200 centimeters. About 6 feet is kind of the limit with this. So we're going to start this up. Go ahead, Stephen. Take this off. Folks, you can see that core of soil in there. And we're just going to take it and slide it out. You can see A horizon, B horizon, and C horizon. A horizon is the organic matter rich topsoil, that humus giving it that dark color. We've got a B horizon, probably a BM horizon. It's a lighter brown color. There's some organic matter in there, but not as much as in the A horizon. And then we've got the C horizon there that contains carbonates. And we could say probably a little bit deeper than that, we're down into the parent material on which this soil was formed. So if we want, then we can go ahead and segment that into the depth increments or the horizons. A horizon in one bag, B horizon in another, C horizon in the other bag. So we can go across a field on this. Oftentimes we do transects across here, or we will sample at random within a zone. So there's you can apply this technique to any type of sampling strategy that you're interested in. So finally, I would like to end off showing you a couple of cores that we took with the hydraulic punch truck from two different slope positions within this field. Which of those cores do you think came from the upslope? And which of those soils do you think came from the foot slope, the depressional area of the field? Well, comparing these two cores, the one core here you can see has a thin A horizon of about 10 centimeters, a B horizon here maybe of about 15 or 20 centimeters, 30 centimeters, and then we're down into the C horizon, starting about there. This one came from the upslope. Actually, it looks very similar to the core we were just talking about that Stephen just took out of the field here just a moment ago. So this is a typical soil profile of an upslope position within the field, a knoll, a shoulder, where we've had relatively little water coming into the soil during soil formation. Some of that water's run off, so it's been drier. Since it's been cultivated, we probably also lost some of that topsoil by erosion downslope. Over here, of course, we have the soil from the depression, from the foot slope, where we have some of that soil that has been eroded by tillage and water erosion, has moved from this upslope down into that depression, contributing to this thicker A horizon. Also more moisture, over soil development, over soil genesis, more moisture, more organic matter additions in that low slope. So in that depression, a thicker A horizon than on the upslope, a thicker B horizon, and we have to go a little bit deeper now before we get into that parent material. So a more fully developed soil profile down in that low slope depressional area within the field. And as we talked about in class, in lecture, what we see there in terms of soil profile development and characteristics that we can see with our eyes translates also into what differences in what we measure in the lab. So that this soil from the upslope, low organic matter content, thin A horizons, low fertility, typically lower available nutrients in this upslope compared to this depressional soil where we've got more organic matter, more reserves of organic matter for mineralization, greater weathering and release of available nutrients into available forms, more fertile, less fertile. And that's something that we take into consideration when we're looking at variable rate and making variable rate fertilizer application prescriptions across landscapes of varying topography.